Okay, so previously we looked at the idea of polar coordinates, and we found the mapping from polar coordinates to Cartesian coordinates and Cartesian coordinates to polar coordinates. So that was just with a point. Okay, we could go between the two. Then we looked at polar graphs, so that was r of theta, so r as some function of theta instead of y as a function of x. And we saw that we had to graph it by going around the circle and looking at the distance from the origin. And we ended up with things like this, okay, like that. So as we go around like this, we have different r values, and then that traces out some kind of loop. Okay, what we're going to look at today is converting graphs between polar coordinates and Cartesian. So we know roughly how to sketch them, but how do we go between the two different coordinate systems? Okay, so let's just write down the transformation for a single point, and then we'll see how to transform the graphs. So remember, if we are given r and theta, then we can convert the polar form into Cartesian form with x is r cos theta and y is r sin theta. Okay, so that was given the polar form, we can convert to Cartesian, or if we are given Cartesian, we can convert to polar, where r is the square root of x squared plus y squared, and theta, that was arctan of y over x. Okay, so that's how we go back and forth with the points. What about going back and forth with graphs? So if you looked in the tutorial, you'd see some of those questions are not converting points from polar to Cartesian, but converting the entire graph from polar to Cartesian, or from Cartesian to polar. So let's do a couple examples. So number one, we have y is equal to x squared. So we know what this looks like in Cartesian form, it's just a parabola. But what does this look like as r as a function of theta? So we're going to make these replacements, okay? So we want to go from Cartesian to polar. So given x and y, this is how we convert. Okay, so y, we want to convert it into polar. So y is going to be r sine theta, and x, that's going to be r cos theta, because we want to go back. So this is going to be r cos theta squared. Okay, so we're using this replacement over here at the top. So x is r cos theta, y is r sin theta. We can substitute it and convert. So here we have r sin theta is equal to r squared cos squared theta. Okay, just distributing that square. Now we've got an r on both sides, so we can get rid of that one over there. So we have one left on that side. We can divide through by cos squared, and we get r is equal to sin theta over cos squared theta. Okay, or we can write it as sin theta sec squared theta. Okay, because 1 over cos is sec, so you can write it like that if you want to. Okay, so this is what the parabola looks like in polar form. So if you were to try and sketch this in polar form, like we did yesterday, you would see that this gives a parabolic shape. Okay, let's look at something else. 2, let's say we have x squared plus y squared is equal to 2x. Okay, so this is some type of circle, but it's been shifted a bit. Okay, you can use completing the square to show that it's a shifted circle. But what we want to do is rewrite this in polar form. So again, we make those replacements. So x, that becomes r cos theta. Okay, y, that becomes r sin theta. And again, x, that becomes r cos theta. Okay, and squared. Okay, so now we can square this out. So we get r squared cos squared theta plus r squared sine squared theta is equal to 2r cos theta. Okay. Now, cos squared plus sine squared, that's going to be 1. So if we factor out this r squared, we get cos squared theta plus sine squared theta, which we know is 1. Okay, so that's 1, so we can get rid of it. Now we have r on both sides, we can get rid of that. So there, that gets rid of the squared. So we get r is equal to 2 cos theta. Okay, so we saw that yesterday. That was one of those circles that we drew. And we ended up with that shifted circle, where we shifted it to the right. So let's start off with this x squared plus y squared equals 2x. We're going to complete the square and show that we also get a shifted circle. Okay, so this is just side work, just to check. So we have x squared plus y squared is equal to 2x. We can take the 2x over, so x squared minus 2x plus y squared is equal to 0. We can complete the square on the x terms, so we're going to have x minus 1 squared. If we expand that out, we're going to get x squared minus 2x plus 1, but we don't want the extra 1, so minus 1, plus y squared is equal to 0. So we end up with x minus 1 squared plus y squared is equal to 1 squared. Okay, and that's just a shifted circle. So it's a circle with radius 1, shifted to the right, which is exactly what we drew yesterday. Okay, but yesterday we were just given this form over here. We sketched it, we got ourselves a shifted circle, and then this just shows us clearly that's what we should have gotten. Okay, let's have a look at some more examples. So number 3, y is equal to x. Okay, so this looks quite simple, but it will show us that graphs in polar form can be a bit different to Cartesian. So here we can write this as r sine theta is equal to r cos theta. Now the r's can cancel, and then we end up with sine theta is equal to cos theta. Okay, but now the problem is there's no r as a function of theta. Okay, so there's a bit of an issue here. But it's not a big problem. We can solve this for theta. So sine theta equals cos theta. We know that this happens when theta is pi over 4. So remember your special angles. At 45 degrees, sine is equal to 1 over root 2, and cos is also equal to 1 over root 2. So they're the same. So what does this mean? Okay, we don't have r as a function of theta, but we have theta is equal to pi over 4. What this means is if we draw our angles here, so 0, pi over 2, pi, and 3 pi over 2, what this equation is telling us is that the angle of whatever graph we have is always pi over 4. Doesn't matter what the radius is, it's always pi over 4. So that's exactly what this line is. This line has the angle pi over 4 for any radius. So we can draw a point here. If I draw the radial line, it makes an angle of pi over 4. This point here, again, it makes an angle of pi over 4. This one over here, this one over here, this one over here, they all have the same angle. So in polar form, if we have a straight line through the origin, we only need to specify the angle. Okay, we don't need to say what the radius is, because all of these different radii here that lie along the line, they all have the same angle. Okay, so we'll just make a note of that. A constant angle, so theta equals pi over 4, theta equals pi over 6, gives us a straight line through the origin. Okay, at that angle. Okay, so if theta is equal to pi over 6, then that means there's a straight line through the origin at pi over 6 radians, or 30 degrees. Okay, so if the radius is not specified, but you are given a constant angle, that just means it's a straight line. All right, any questions on that? Okay, let's do something a little bit more complicated. So number 4, y is equal to x squared plus x plus 1. Okay, so we've got a parabola, different to the one that we had before, so it's a bit more complicated. What does this look like in polar form? So as we did before, we're going to make the substitution. So we get r sine theta is equal to r cos theta squared plus r cos theta plus 1. Okay, now we can square that term. We get r sine theta is equal to r squared cos squared theta plus r cos theta plus 1. Okay, now we don't want to leave it in this form. We want a function r of theta, like we want a graph y of x. So let's take all the terms to one side. So we're going to have 0 is equal to r squared cos squared theta plus r cos theta minus sine theta plus 1. And then we'll see now on the right-hand side that this is a quadratic in terms of r. We've got r squared, we've got r, and we've got our constant. So if we want to solve for r, we can just use the quadratic formula. Okay, so solving for r. Okay, so r is equal to minus b, so that will be minus cos theta minus sine theta, plus or minus the square root of b squared, so cos theta minus sine theta squared, so that's b squared, minus 4ac, so minus 4 cos squared theta, all over 2a, so that's 2 cos squared theta. Okay, you can then simplify that if you want, but I'm just going to leave it like that. So here we see that it's very complicated, okay? But the reason it's complicated is because we started with something that is simple in Cartesian form, and we're converting it into polar, but it doesn't work well with polar. Remember what polar coordinates are. So polar coordinates are something like this. We've got this radius and an angle. Okay, so polar form works well if something is moving around a point, right, at some distance with some angle. So graphs like that. Okay, so if you have a curve that makes a loop around, the distance to the origin changes, so it's still a loop like this. This is good in polar coordinates. Okay, however, if we convert this into Cartesian, it might look complicated because we're going to have x squareds and y squareds and so on. Here, we took something that's simple in Cartesian and tried to convert it to polar, so it's going to look more complicated. Okay, so the idea behind that is sometimes it's better to work in Cartesian coordinates, sometimes it's better to work in polar coordinates, and you should know how to go between the two. Okay, just a final example on this. Let's say we have r is equal to 2, so that's very simple in polar coordinates. R equals 2, that just means we've got a circle of radius 2. So for any angle going around, the distance is the same. But that's exactly what a circle is. Okay, so it's very simple looking in polar coordinates. In Cartesian, it's going to be x squared plus y squared is equal to 2 squared. It's a bit more complicated. So sometimes polar coordinates are simple, sometimes Cartesian is simple. You should know which ones to work with. Okay, and if you're doing physics, this comes up quite a lot if you're doing circular motion. Things moving around in a circle or things moving around in a loop, it's better to work in polar coordinates. So for example, if you're studying like the planets going around the sun, it's doing a loop around the sun, so polar coordinates would be better. Okay, because you've got the origin at the sun and you're looking at the distance of, say, Earth to the sun as it goes around. Okay, polar coordinates would be better for that. Trying to do that problem in Cartesian is just a mess. Okay, so you should be able to know which ones to work in and how to go between the two. Okay, any questions on this? Yes? So once you've done your substitution, like here for example 4, once you substitute, it's just up to you to solve for r depending on what you're given. So you might have something like this, where it's r squared and r and so on, then you use the quadratic formula, okay, because we're just solving for r. If it's something else like this, okay, this was quite simple, we just get r equals 2 cos theta. So sometimes it's easy to solve for r, other times you have to use completing the square or quadratic formula. It's whatever algebra you need to do. For this one, we get r squared on the left hand side, r on the right. We cancel it and then we solve. Number 4, quadratic formula, like I said. So here we've got r squared, r and a constant. So that's like ax squared plus bx plus c, and then this is just the quadratic formula. Okay, so again, it depends on what you're given. Okay, any other questions on this? Okay, let's look at one more example. So let's say we have y is equal to 1 over x plus x squared. Okay, so a hyperbola added to a parabola. We want to know what does this look like in polar form. So instead of y as a function of x, we want r as a function of theta. So we make our substitution as we've been doing. So r sine theta, and we have 1 over r cos theta plus r squared cos squared theta. Okay, so we end up with something like that. Now, again as before, we want to solve for r. We want r as a function of theta, so we want r of theta. Now we've got an r on the left-hand side, 1 over r here on the right-hand side, and r squared. So it's a bit difficult to work with. Let's multiply through by r times cos theta to get rid of that fraction. So this will become r squared sine theta cos theta is equal to 1. And again, this will be r cubed cos cubed theta. Okay. So now, again, it's a bit more difficult than last time because we've got this r squared and r cubed. So let's take everything over to one side. So we're going to have r cubed cos cubed theta minus r squared sine theta cos theta plus 1. Okay, so we've got something like this. So once it's in this form, we just need to figure out a way of solving for r. So here it's a bit more complicated because it's r cubed and r squared. But once you solve for r, we can end up with something like r of theta. Okay, so this is a little bit complicated to do, but not so bad. I'll put it for homework. Okay, so you can practice your algebra. Okay, so everything you need to know is just substituting. Okay, so if you have y, you substitute r sine theta. If you have x, you substitute r cos theta. Everything else is just high school algebra. Okay, so solving for r, trig, all of that, that's just high school level work. Okay, so from here again, we just want to solve for r. Okay, any questions on that? Okay, so just a bit of algebra here. It's not so easy, so I'll put quite a few points for this homework problem. Okay. All right, any other questions on this? Okay, so there's more questions in the tutorial going both ways. So you'll be either given a equation in Cartesian coordinates and you want to convert into polar, or you're given polar form and you want to convert to Cartesian. So here we started off with Cartesian and we wanted to go to polar. Now we're going to look at, given a polar form, what is the Cartesian form? Okay, again, you should be able to go both ways with that. Okay, so next part, given a polar form, what is the Cartesian form? Okay, like before, we're going to start off with a simple example just to show what to do, and then we'll do some more complicated ones. So let's say r is equal to 2 sine theta. Okay, you should have an idea of what this is from last time. So when we sketched this, we got ourselves a circle. So when we convert from this polar form to Cartesian form, we should also get a circle. Okay, so what do we do? Now, just substituting for the change of coordinates, that's a bit difficult to do. You can. So we can substitute r is the square root of x squared plus y squared, and theta is tan inverse y over x. You can do that. You'll get the same answer, but that requires a bit too much working. So we're going to try to find a way to avoid all of that. Okay, so what we can do is multiply both sides by r. So we're going to have r squared is 2r sine theta. Okay, so why did I do that? Look at the left-hand side, we have r squared. We know from Pythag that that's going to be x squared plus y squared. On the right-hand side, we now have r sine theta, but r sine theta is y. So you see, by multiplying both sides by r, we simplified our work, because now r squared, that's just x squared plus y squared, and on the other side, that's just 2y. Okay, so instead of substituting r as the square root of x squared plus y squared, and substituting theta as arctan y over x, okay, you can do the work, it's not so bad, but it's a lot more work. Here, we just multiply both sides by r, that's one step, and then we're done. Okay, so please don't do the long way if there are shortcuts available, especially with tests. You don't want to spend so long on a question. If you know a shortcut, right, it will help a lot. Okay, so this doesn't look so much like a circle, but we can do completing the square again. So we're going to have x squared plus y squared minus 2y is equal to 0. We can complete the square on y, so we get x squared plus y minus 1 squared. If we expand this out, we get y squared minus 2y plus 1. We don't want the extra plus 1, so we minus 1, and this is equal to 0. Now this one we can take over to the other side. we get x squared plus y minus 1 squared is equal to 1 squared. Okay, and that's the usual form of a circle that we know. So remember, x minus a squared plus y minus b squared is equal to r squared. Okay, so now we can see very clearly it's a shifted circle. Okay, any questions on this example? Okay, let's look at another one. So r is equal to 2 sec theta. Okay, so now we've got sec. That's not one of those fundamental ratios. Okay, we'd rather work with cos. So instead of sec, let's write it as 1 over cos. Okay, it's better to work with sine and cosine. So if you're ever given sec or cosec or tan or cotan or any of those, convert to sine and cos, because we know that cos, that's eventually going to become x, and sine, that's eventually going to become y. So it's best to convert. Now we can multiply both sides by cos. We get r cos theta is equal to 2. Okay, but then r cos theta, that's just x. So we get the equation x is equal to 2. So a little sketch of what's going on here. Okay, if we have the polar form r is equal to 2 sec theta, if we substitute theta equals 0, sec theta is going to be 1, so r is equal to 2, which means we're over here. And then as we increase sec theta, r is going to go to infinity. So here we're going to end up over there, then over there, over there, over there. Okay, all along this vertical line, up to infinity when we substitute pi over 2. And then if we substitute negative angles, so if we go this way, so if you go counterclockwise, that's positive angles. If you go clockwise, that's negative. We end up going down here like that. Okay, we move down the line. Okay. So that's just a quick diagram of why this gives us x equals 2. Okay, last example for this, let's say r is equal to tan theta. Okay, again, if we ever have something that's not sine or cosine, we should convert. So this is going to be r is equal to sine theta over cos theta. Okay, now we want to try get this into a form with x and y. So let's start by multiplying both sides by cos. So we get r cos theta is equal to sine theta. Okay, now this one's going to be a bit more complicated than before, but it's not so bad. We've got r cos theta. We know that's going to be x, that's fine. But on the right, we just have sine theta. Okay, we can't convert that to y because we need r sine theta. So let's multiply both sides by r. Okay, so now we've got the r, we're going to deal with that soon. R cos theta, that's going to be x. R sine theta, that's going to be y. So r, we kind of stuck with that, so let's just substitute what r is. That's going to be the square root of x squared plus y squared. Okay, r cos theta, that's going to be x, and r sine theta, that's going to be y. Now, if we can solve for y, let's do that. So let's square both sides to get rid of that root. So it's going to be x squared plus y squared is equal to y squared. Okay, we can distribute. So this gives us x to the 4 plus x squared y squared is equal to y squared. We can take that over to the other side. So we get x to the 4 is equal to y squared minus x squared y squared. Okay, again, just keep in mind, we're trying to solve for y. So we end up with x to the 4 is equal to y squared 1 minus x squared. Okay, we can divide through by that. So y squared is x to the 4 over 1 minus x squared. Finally, we can take the square root, and we get y is equal to plus or minus x squared over the square root of 1 minus x squared. Okay, so the plus part, that will take care of the top portion of the graph, and the minus part, that will take care of the bottom portion. Because remember how these work. If it's r of theta, we're going to end up with something like that. Right? It's always going to be some loop, something like that. But if we're converting into Cartesian, we're going to have a top part. That's this bit. Okay, and we have a bottom part. Okay, so there's two parts. You can't have a single y equals something that handles both. So y by itself can't give you a positive and a negative answer. We need two parts. So y equals plus something, that will be the top part. Y equals minus something, that will be the bottom part. Okay, so you'll see that occasionally. You'll have a top part and a bottom part to it. Okay, any questions on that? Yes? Which one? Which line? Over here. Oops, sorry. Let's put the over here and over here. I just multiplied both sides by that. Now, I explained we've got sine theta on the right-hand side, but we want to convert it into y. But y is r sine theta, so we need a r there. Okay, same if we had a cos theta by itself. If we want to convert that into x, it needs to be r cos theta. So here, I'll just make a note. So here, r sine theta is y. Okay, we need that there. And r cos theta is x. Again, we need that there. Okay. Is that all right? Okay, sure. Okay, any other questions? Okay, so that is converting between polar graphs and Cartesian graphs. Just before we go, I just would like to introduce what we're going to be doing next week, and that is conic sections. Okay, so with conic sections, we need to imagine a cone. Okay, so we've got something like this. Okay, so imagine we've got this double-sided cone, and we're going to cut it at different angles. So if we cut it like this, okay, just horizontally, if you have a cone and you cut it horizontally, the cross-section part there is a circle. So imagine you've got a cone, you cut it, you end up with a circle. If you cut it at an angle like this, so you've got your cone, you cut it at an angle, the shape that's produced is a parabola. Okay, so you can look at this online. There might be some nice videos on that. If you cut it at an angle, you get a parabola. And then if you cut it vertically, so vertically like that, you end up with two hyperbola. You know, like the 1 over x things. So if I take a cone and I cut it different ways, I end up with a circle or a parabola, or a hyperbola. Okay, so I will post some video links to show you this, and it shows you nicely the cutting process. So the idea of conic sections is to take these three different graphs, or these three different shapes, and unify it in some way. So instead of treating them separately, we're going to have a way of treating all of them the same. Okay, so the circle and the parabola and the hyperbola, okay, with the asymptotes like this, we'll see that these are just three variations on the same thing. Okay, so we have one thing called a conic section with some parameter we'll see called the eccentricity. If we change that parameter, we go from circles to parabolas. If we change it some more, we go from parabolas to hyperbolas. Okay, so it's a way of unifying these three things. Okay, and then we'll look at some geometry of these. So if you want to look up some things now, we're going to go through what's called the focus of the shape, the minor and major axis of the shape, and the vertices of the shape. Okay, so if you just look that up online, you'll see what I mean with that, but we're going to look at that next week. Okay, those that are doing physics, if you look at planetary motion, that uses a lot of this. If you look at something called scattering, so if you have some object and you have some incoming particle and it bounces off, that's going to produce parabolic or hyperbolic motion, so it's used there as well. Okay, so it's used in quite a few places. It's important to understand where it comes from. Okay, but that will be saved for next week. Okay, so the tutorial test for Thursday, that will be just on this polar coordinate stuff. Okay, so none of the conic sections. Okay, yes? Sorry, the multiple choice? Yeah, so the multiple choice and the tutorial test, they will alternate. So last week we had multiple choice. Okay, this week it will be written like a normal test, and then next, the week after, it will go back to multiple choice. Okay. Sorry? Extend the time. I can't extend that, sorry. The way it works with the university is each assessment has to have a fixed amount of time, so that the total amount of time is fixed. Like with tests, if it's 45 marks, it's like 45 minutes, and then you write 3 tests. With the tutorial test, it's like half an hour each, and if you add it all up, it must be a fixed amount of time. Okay. Also with that time, with the timing, with the test, again, it's a fixed amount of time. So you can't do it slowly. Okay, you need to be quick going through that. So I can't give you an hour to do the TUT test, and then you can't finish the test. Okay, so it needs to be fair with both of that. Okay, but half an hour should be plenty. It's only, I think, 2 or 3 questions. Okay, exactly the same as the tutorial. Whatever the tutorial work is, that's what's in the TUT test. Okay. Any other questions? Okay, so I'll see you in the tutorial.